Okay, so there are some questions like those are based on the electromagnetic induction. There's a chapter name. The topic is motional EMF. So let's start with the first question. There's a uniform magnetic field B normal to the XY plane. A conductor ABC has length AB is equal to L1. Parallel to the x-axis, length BC is L2. Parallel to the y-axis. ABC moves on XY plane with this one. Okay. So here this like kind of a conductor ABC moving in Vx and Vy direction, right? The potential difference between A and C is proportional to. So you can see here there are like two wires A, B and C, and this whole system is moving with Vx horizontally, Vy vertically. So first of all, if you see that AB wire, so AB wire is moving with Vx horizontally, Vy vertically. So we know like from the motional EMF that because of Vx there will be no induced EMF across AB, right? Because we know like when V is parallel to L vector, the induced EMF is 0. So which velocity will induce EMF across AB? Vy. So because of Vy, that be an induced EMF, and because of that the A will be at high potential. So you can write Va minus Vb is equal to VBL, right? That is the formula. So V by Vy into magnetic field into AB length is L1. Okay, now just focus on BC. So BC wire is again moving with Vx and Vy. So this time because of Vy, that BC, there will be no induced EMF across BC because again that this condition is there. So we'll see Vx only. So this one is moving with Vx. So this time that the C will be at high potential, B will be at low potential. So Vc minus Vp is equal to Vx BL2. Now we need to find the proportional potential difference between A and C, right? So between A and C means like Va minus Vc. So I have to subtract them. So Vy L1 minus Vx L2 into B. So we can say that Va minus Vc is directly proportional to this one, Vy L1 minus Vx L2, and that is right. That is nothing but C option. So C option is correct here. Okay. The minus sign could be like can come, okay, based on like the direction of magnetic field. Okay, it's not mentioned clearly. The magnetic field is outward or like inward. So I assume like magnetic field is inward. So that's why. So, but proportional we need to find. So that is the correct option. So C is correct here. Okay. So let's move to the next question. Okay, so this is the next second question. Two conducting rings of radius R2R move in opposite directions with velocity 2v and v respectively on a conducting surface S. There's a magnetic field perpendicular to the plane rings. So I will assume, okay, it is given. Okay, so the magnetic field is into the plane. The potential difference between the highest points of the two rings. Okay, so let's say there are points here. This point is P here, this point is Q, this is S, this is S. As it is given that the horizontal surface, okay, that is a conducting surface. That means potential at S will be equal to potential at this point. So potential will be same because we know the conducting surface is equipotential surface. The potential on this conducting surface will be same everywhere. Now if you see like potential induced EMF across this ring P, right? So what is that induced EMF across a ring? So we know like VBL, where L will be the displacement vector. So in the case of ring, okay, we'll be taking as the diameter. Okay. So in this case, so if you take a diameter here, so potential difference basically. The potential, so this is P point here, this is S point here, and it's moving in this direction with 2v. Okay. So what is the induced EMF here? Okay, in between P and S, you can like use the right hand thumb rule and you can see that S is at high potential. So Vs minus VPL, right, which is VBL. So 2VB into 2R. R is the radius, so diameter is 2R. Similarly, for that bigger ring, this is Q, this is S, and it is moving with V. So this time VQ minus VS, this Q will be at high potential, and again VBL, VB, and 4R. Now to find potential difference between highest point means VQ minus VP, so we have to add them. So you can add here, so 4 VBR plus 4 VBR, that is 8 VBR. So that is the potential difference between the highest points of the rings, and option D is correct here. Okay, so hope you understood this one. Let's move to the next question. Okay, so next question, the third question, right? Yeah. So third question is, the magnetic field in a region is given by B vector equal to B naught 1 plus H by A K cap, and there is a square loop. The square loop is placed along the x-axis and y-axis here, and the magnetic field is in outward direction, but it varies with h, and the loop has a velocity v naught I cap. So we can say like this 0, 0. So there's a magnetic field changing basically. The magnetic field is not constant within the loop here. So whenever there's a magnetic field varies within the loop, okay, so the process of calculating the induced EMF through flux. So flux equal to B into A. So what is the magnetic field here at this instant? 1 plus H by A into, the side is D, so area will be D square. Now d phi by dt is equal to B naught D square 0 plus 1 by A dH by dt. That's the differentiation I did here. I hope you understood this one. dH by dt is nothing but velocity, and this is induced EMF. So induced EMF is coming as B naught D square V naught divided by A. That's it. Okay. So that is the process to calculate induced EMF whenever there is a magnetic field changes within the loop. Okay. So according to the option A is correct. Clear? So hope you understood. Let's move to the next question. Okay, so next question, the fourth one. When magnetic flux through a coil is changed, the variation of induced current in the coil with the time is shown as in the graph. The resistance of the coil is 10. The total change in flux of the coil will be. So we know like there's a relation between delta Q and delta phi. So I hope you know this relation. So delta phi is equal to R delta Q, and the delta Q is a charge flown which can be written as integration I dt. Right, that is like relation from the delta Q and current. Okay, from the current electricity. Delta Q is equal to integration I dt. So I use this formula here. So delta phi is equal to I. Okay, now the I, as you can see, the I is a variable. So we'll write the expression of this I. So this is straight line here, which we can write the equation of the straight line. So I is equal to 4 minus, the slope is 4 by 0.1 into t. So C minus mx. Okay, mx plus C I used here. So I is equal to 4 minus 40 into t. So I'll use this value here, 4 minus 40t, and into dt limit 0 to 0.1. Okay, so we'll integrate this one, and that will be your answer. 4t minus 40t square by 2, 0 to 0.1. R, so it becomes like 4 into 0.4 minus 20 into 0.01. So delta phi R is given 10 into 0.4 minus 0.2. So delta phi is equal to 10 into 0.2, which is equal to 2 Weber. And that is the answer. Okay, so it's kind of a like good question, right? So where we like calculate the change in flux, okay, if current is a variable. Okay, so the answer of this question is 2. So it's a like integer question. Okay, let's move to the next question. Okay, next question, the question number 5. A conducting rod PQ of length 5 meter oriented as shown in figure, moving with v velocity without rotation. The induced EMF in the rod is, so here the rod is 5 meter, which is making 53° angle. So this is the length of the rod, which is moving with v velocity. So v is given as 2 I cap, magnetic field is given as 3 j cap plus 4 k cap. So we know the induced EMF is v cross b dot L vector. We know like this point will be at high potential, this will be at low potential. So VPQ, right? and in this direction will take as L vector. Okay, so now here V cross B. Okay, so V cross B will find first. So what is V cross B here? So 2I cross 3J plus 4K. Now you just do the simple cross product. I cross JK and I cross K is minus J. So this is V cross B. And what is L vector? So for L vector you can take the component, which is 5 cos 53 I cap plus 5 sin 53 JK. So I just took the component here. Okay. So 5 cos 53, 3 by 5, 3 I cap plus 4 J cap. Now this is L vector, this is V cross B. Now do the dot product. So 6 K cap minus 8 J cap dot 3 I cap plus 4 J cap. So dot product is straightforward. So what is it here? So just see the same dot products vectors. So it is minus 32. Okay, so magnitude is 32. So 32 volt is the answer. Okay, so that's it. Let's move to the next question. Okay, so this is the sixth question now. A rectangular loop with a sliding connector of length 1 meter situated in a uniform magnetic field. So resistance of connector is 2 ohm. The resistance, it's okay. Find the external force required to keep the connector moving with the constant. Okay, so if you know like this topic, right, so we know like there will be a force acting on the slider, right? So that's what we need to find here. So let's say, so first of all, the slider has a v velocity in this direction, so that will be that means this will be at high potential, this will be at low potential. So I imagine a battery here, and there's a resistor also given, connector 2 ohm. So this can be considered as an internal resistance. And with this resistor is connected 6 ohm and there's a 3 ohm. So if you draw the diagram, so we'll find out that this is like kind of a current electricity problem. We need to find the current in this connector. Okay, so for that you can see the 6 ohm and 3 ohm are in parallel combination. So that means 2 resistors are in parallel, so 6 and 3. So R equivalent of these two will be 2. And that 2 will be in series with this one, right? So this is 2 ohm, this is 2 ohm, this is C. Now what, so total, so what is R equivalent of the circuit? 2 plus 2, now they are in series, so R equivalent is 4 ohm. So current in the circuit is E by 4, E is VBL, which is 4, that by 4, so VBL, so just see V value is 2, magnetic field is 2, length is 1, divided by 4, so it is 1 ampere. So everything is given. You just see the question. Now this current is flowing in this direction, right, upward. Now because of the current there will be a force acting, because this wire, this is a current carrying wire now, which is placed in a magnetic field which is like kind of inward, right? So if a magnetic field is inward, so the force on this one will be left hand side. So there is a force acting. The point is like, if we do not apply any other force, so this will become a retardation. The velocity of the the velocity of the wire will keep on decreasing, because the velocity is forward direction and the force is at an opposite direction. So velocity will keep on decreasing. But the question says that find the external force, like, okay, from our side we need to apply to keep the connector moving with a constant velocity. That means the same amount of force will be acting in opposite direction. So net force will be 0, acceleration will be 0, so that the wire can move with a constant velocity. So that means we just need to find the force acting on it, and that will be our answer. So force on a current carrying wire is ILB. So force I is 1, L is 1, magnetic field is 2. So which means 2 Newton. That's it. So that is your answer. The answer of this question is 2 Newton. That's it. Okay, so hope you understood this question. Let's move to the next question. Okay, so now this is the 7th question. So here again the loop is moving, okay, in this direction, and there's a magnetic field which again is variable. Okay, so this is again this example of that question. That loop is moving, okay, in a variable field. So what is the process? So I'll tell you the process here. So you find the flux. From the flux you flux you find B into A. where B is the variable here. From the flux you differentiate and you find the induced EMF. So that is the process. So I've already done. So you try to do with that process. Okay, just stop the video and just try to do it. I'll tell you another method. Another method is like we need to find induced EMF at this instant. So at this instant we can see here there's a loop here which is moving this direction. So there are P, Q, R, S. 4 wires are present. QR and SP are in the direction of velocity, so that means there will be no induced EMF across QR and SP. So EQR equal to ESP is equal to 0. But if you see that PQ and RS, right, they are moving. This is H, this is A. So at this instant, like we can imagine a battery here. So in both the cases RS and QP, you can see that R will be at high potential, S low, Q is at high, P is low. So if I imagine a battery here, so one battery will be like this and one battery will be like this. Correct? The induced EMF will be different because the magnetic field is different here. So I'm going to write the induced EMF now. So if I write the induced EMF for this left battery PQ, so what is the magnetic field here? So magnetic field is, so let's say E1 and E2 I'm writing. So E1 is VBL, so V mu naught I by 2 pi H into A. Correct? And what is E2? V mu naught I by 2 pi H plus A into A. These two batteries are in series. Okay, if they are equal, just like normally what happens here, if I say the magnetic field is constant, so induced EMF will become 0. You have studied that one, right? But here that E2 and E1 are not seen. So that means the induced EMF is not 0. So induced EMF क्या हो जाएगा? E2 minus E1, right? E1 minus E2 because E1 is more than E2, right? So now you just put these values here and that will be your answer. And whatever data is given in the question, just put the value. So that's I'm leaving on you because there's a calculations are there. So I suggest like you try to do this calculation, okay, by yourself, right? Just do the calculation here, put the values, answer I'll tell. So answer will be coming as 1.7, approx will come into 10 to power minus 5 volt. Okay, just try to do it. Okay, I'm leaving this as an homework. Okay, sure. So let's move to the next question now. Okay, so this will be our last question in this series. The question is, a rectangular loop of dimensions L and W, resistance R, move the constant velocity V. It continues to move with the same speed through a region containing a magnetic field. Okay, the distance is 3W. Sketch. Okay, we have to draw that graph here: flux, induced EMF, and external force acting on the loop as a function of the distance. So let's talk about the first flux. Okay, because from the flux we'll calculate the induced EMF, and once induced EMF is there, current and then force. So first of all, you think about, just stop the video and just think about it, how the flux will be changing, okay, when it is moving. Okay, so let's see here now. So when this loop, okay, it is entering here at this position, so some of the electric field is present in the loop. So that as it moves forward, the magnetic field inside the loop will increase, and more field lines will be entering. Yeah, or you can say more and more field lines. Okay, right now you can see 1 and 2 only, but when it moves forward, so like after some time it will be like this, it will be shifted. So you can see that so many field lines now. That means the magnetic field into the plane is increased. So my flux is changed. So if flux is changing, in EMF will be induced. Now flux, how the flux is changing? So you can see here the flux V is moving with the loop is moving with the constant velocity. So we can say here that magnetic field is increasing with a constant rate. And like phi is equal to, the phi is equal to B into A, and B is basically increasing with a constant rate, right? B is increasing with a constant rate, or like area is like where the flux is changing. Okay, so you'll find that the flux is increasing at a constant rate. So now if we draw the diagram, the graph, so and till when the flux will keep on changing, keep on increasing, the moment when this entire loop, okay, fits inside the magnetic field region. So from this moment to this moment, the flux will keep on increasing with a constant rate because it's moving at constant speed. So how the graph? So we'll be having a graph a straight line. Okay, because magnetic field is increasing, okay, the constant rate here. So we'll be having a the straight line graph. Now afterwards, when the loop is completely inside and the width of that region is 3W and its width is W only. So for the time being, okay, as it is moving continuously, for a time being, as it reaches to this side, there will be no change in flux. So that means flux is constant, kind of, right? So if flux is constant, we'll be getting as this one. And afterwards, when it's coming out, the flux inside the field, inside the plane is decreasing. The flux will be decreasing. And finally, when that loop comes out completely, again the flux becomes 0. So this is the graph of phi versus t. Clear? अब induced EMF क्या हो जाएगा? तो E is equal to minus d phi by dt. So you can see here from 0 to T1, T2 and this T3. So 0 to T1, the phi is increasing at a constant rate. The slope is basically that E is nothing but the slope of flux time graph, so which is constant but in negative. So if you draw the graph E versus T, so there will be negative side. Okay, so slope, so slope is constant. So from 0 to T1, slope is constant, so induced EMF is constant, and because of this minus sign, it's coming in minus. Now T1 to T2, flux is constant, that means induced EMF is 0, so there will be no graph, and afterwards becomes again constant, positive side. Okay, because now this time flux is decreasing, slope is negative. So if slope is negative, 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 positive, so we'll be getting a induced EMF positive constant. So this is EMF graph. And the last we have the force graph. A force will be coming like on the current carrying wire which is inside this one, right? And that force will be present only when the current is there. So first of all, from T1 to T2, there is no current, so that means there is no force in that one. I know that we can simply say the current is absent, current is 0, so force is 0. Now focus on 0 to T1. So 0 to T1, that induced EMF is constant, so that means a constant current is flowing. So if there is a constant current flowing, I is equal to E by R, so F will be equal to ILB. So everything is constant here. That means like the force and direction, if you see, the direction will be so this will be at high potential, this will be at low potential, the force will be left hand side, but they are asking external force. So similar to the last question now, so the external force will be acting in opposite direction, that means in positive direction. So we'll be having a graph in positive side but constant, then 0, and last again when it's coming out, when it's coming out, so when it's coming out, the induced EMF is positive, okay, not an issue. But when it's coming out, again there will be current flow, again this will be moving with V, and this will be positive negative. Means the positive negative will not change whether this insert, whether it enters or like exit. So when positive negative does not change, that means still the force, external force, will be in this direction, so will be positive again. The direction of force is not changing to 0 to T. So this is the graph of external force versus time, induced EMF versus time, flux versus time. So I hope you understood. You can try one homework I am giving, that try the graph of current versus time. Okay, and similar question is being asked in JEE Advanced also. Okay, you can try like the JEE Advanced PYQ now. Okay, so hope you understood, and with this question I end this session. Hope you find it useful for your test preparation. Thank you for watching.